the function, the thing which replaces x, is called the argument of the function. Huh? Oh, okay. So it's called the argument. You'll hear this, again, more as you proceed through math. You'll hear that terminology. But what's the argument of this function? And so we're talking about the thing that you're plugging in. So what's the argument of part A?
-2.
The argument of part D?
-3x.
And the argument of F? X plus H. Okay? All right, finding domains algebraically. So we talked about how we can tell if a relationship is a function by checking and seeing whether or not it works. But what about domains? So just remember, when you're given a function, we need to investigate where the function is defined. And some things that we'll have to take note of in this class is, do you ever have division by 0? You can't have that, right? So we'll always need to be checking our functions to make sure they never get division by 0. And also, you need to ask yourself, do you ever get a negative value under the square root? Or any even root, because we cannot have a negative value underneath the root. An important note here, always check for domains prior to algebraic simplification, and I will explain that later. So here are some examples. These are definitely good problems. You definitely will see these types of things on a test. All right? So part A. F of x equals, was that a question, Giovanna? Okay. All right. The question is to find the domain of f. And not only do I want the domain, I want the domain in interval notation. I didn't say that up here, but we'll put it in interval notation at the end. So what I'm asking is, tell me the x's that you're allowed to plug in here. So if there's something you can't plug in, I need to know that somehow. So what are the two things that we always look for, at least in a college algebra class, the things that we look for? Division by 0, right? Can't have that. And can't have negatives under roots. We actually have both situations here, don't we? There is a possibility we could get division by 0. So what I'm going to do is I'm going to look at the bottom. I need to make sure that that's never 0, right? So what I'm going to do is almost like a reverse process. If I want to know when that's not, if I want to take out the things that will make it 0, I'm going to first figure out what makes it 0. And then I'll make sure I exclude those from my answer. So I'm going to take the denominator and set it equal to 0. And that's standard protocol when you have a function that has a fraction in it where your denominator has x's. So I'm going to take my denominator, set it equal to 0. And then this is just a linear equation. You get -4, right? If x is -4, I've got problems, right? I could not plug -4 into this. So don't want this, right? Don't want it. Just remember what we're doing here. We're solving this. We're not saying the answer is -4. We're saying that's a value that we want to chunk. We want to throw it out of our domain. All right, that's one issue we have, all right? So we're done with the denominator? Yes? The other issue is we have a square root. And we know that when we have a square root, we cannot have a negative under there. What's another way of saying we can't have a negative? What can we have? Positives? Greater than? 0. Or what? Or equal to 0. Right? If I say you can't be negative, you obviously could be greater than 0. But you could also be 0. 0 is not a negative number. Is 0 a positive number? It's neither one. All right? 0 is neither positive nor negative. It's the only number that's that way. Yes?
If you were to plug 0 into the square root, it would be -1.
That's correct. But listen to what I'm saying. We need what's underneath the root to be greater than or equal to 0, right? I'm not saying we need x to be greater than or equal to 0. So with my wording, when I say we want everything under here, we need this thing to be greater than or equal to 0. That's called the radicand. The radicand is the thing that is underneath the root. It's a radical symbol. The thing inside of it is called the radicand. That needs to be greater than or equal to 0, right? That's what I want to happen. So I'm just going to replace the radicand here as what? X minus 1 greater than or equal to 0, like that. What type of equation did we have here when we were doing this problem? Linear equation. Anybody know what this is called? It's not a linear equation. Is it? Okay, who's that? What's your name? You don't, Matthew? You didn't bring your thing again? Oh, you have? Okay, put it up because I still don't know your name. Thank you, Matthew. All right, so this is called an inequality, and it's a linear inequality. So to solve linear inequalities, it's pretty easy to do. You treat it just like an equation. You move this one, you isolate the x. What's the one thing, does anyone remember the one thing you have to be careful with linear inequalities? There's a case where sometimes that flips over. Do you remember that? When does that happen when that flips over? When you multiply or divide both sides of it by a negative number. For example, if I had negative x is greater than or equal to 2, and I want to turn that into a positive x, I'd multiply by negative 1 on both sides, right? If I do that, multiply this side by negative 1, I get x. Multiply this side by negative 1, I get negative 2, but the inequality flips. So inequalities you have to be very careful with. But that's not the case here, because all we had to do was move, add, not multiply, add 1 to both sides. Why did I put 0? Add 1 to both sides, and we get this. And this we want, right? We want that. We want x to be bigger than or equal to 1. Okay, so now I need the answer, and I need it in interval notation. So what I like to do is draw a number line. Okay, I'm going to draw a number line to try and represent this domain. So here is a number line. Here's 0. The first part we did said we do not want negative 4, right? We don't want it. So I'm going to go out here to negative 4, negative 1, negative 2, negative 3, negative 4. I don't want it. So what I'm going to do is I'm going to put this right here like that. That open hole, right, that circle means do not include negative 4. Please do not put that as part of your answers. But I can have anything else I want, right? Okay, so anything else I want is okay. But this one says what? I need to be greater than or equal to 1. So I go to 1 on the x-axis, and I say greater than means which way? To the left or to the right of it? Right. To the right. So I actually need to be greater than 1 or equal to 1, which means I fill that dot in solid. Or that's exactly what I was going to say next. You may have seen books or another class where they put a bracket there instead to say, look, it's everything from 1 over. So let's see, we need to put these two ideas together. This says, hey, just don't be negative 4, right? This says we have to be bigger than or equal to 1. So what is that together? What's our domain going to be if we put those two ideas together?
X, so that X.
Everything greater than or equal to 1, right? Could I be something here? No. I mean, it would be okay with this, right? This says just don't be negative 4. So that would be okay. But this says we have to be bigger than or equal to 1. So we couldn't have that. So nothing over here works, right? Just from 1 on. How do we write that in interval notation? 1 and then infinity, right? But we need a little more. Bracket on the 1.
Then a squiggly thing on the other.
parenthesis on infinity. You always put a parenthesis on infinity. Always, always, always. And some of you may have seen something like this. X. It's like this weird little E looking thing. No? Okay, what that means is X is an element of this interval. I'm sorry?
Is this how you want it?
No, I'm just, if you see it in the book that way, or if you see it later on in your math career, you'll know what that symbol means. This is, X is an element of that interval. So you have an interval, that's your basket, right? Remember X, we said the domain was a basket. Your basket is all the numbers from 1 to infinity. Questions? Okay, we need to move on. We need to go a little faster. How about part B? Are there any problems there? Do you see any fractions where you might get division by 0? No. Do you see any square roots? No. So if you don't see square roots and you don't see fractions, then pretty much you don't have any issues, which means you're free to plug anything in. So how do we say anything? We can do, in interval notation, for part B, the answer would be X is an element of, but I'm not going to write it, negative infinity to infinity. And beyond, yes. It's hard for me not to get distracted in classes like this, but I'll show you something real quick. That didn't work. Okay, how many sides does this surface have? Will we agree that this would be like a two-sided surface? I know some of you might be, but what about that edge? And let's just say this is two sides, okay? Right? Two sides, everyone okay? All right. Now, what I'm going to do is, and I wish this were a little bit thinner. Okay, so this is still two sides. And I could justify that reasoning by saying, okay, I'm going to put my index finger on one side, I'm going to put my thumb on the other now. Each finger is on one side of that page, right? Okay, so now what I'm going to do, I'm going to take this, and I'm just going to twist it one time, and I'm going to paste these two edges together like this. All right, so I've created this. Do y'all see that? Anyone know what this is called? No? This is called a Mobius strip. All right, a Mobius strip. Now, what I would like to point out is that how many sides does this have? It actually has one side. So if you follow my index finger around and come back through, you'll actually be where my thumb is, and then you keep going around and you go, and you're going to come back to the index finger and then back to the thumb and back. So now my thumb and my index finger are on the same side of this, which means there's only one side. So the Mobius strip is an example of a single-sided surface, which is kind of weird. Now, if you were to start walking along here, right, you would just keep walking, wouldn't you, forever? Where if I took it apart and put it out like this, two-sided surface, if I started walking, I would come to an end, right? But by the Mobius strip, I create that sort of infinite loop, right? Kind of? Anyways. It's kind of that symbol comes from that sort of concept of. All right, part C. I will mention that I will always accept this. I know that's not interval notation, but I would always accept this on a test for all real numbers, for everything. Double script R, double struck R would be okay with me. Okay, C. Do we have any issues with C? You have a fraction, so you have to look at the denominator, right? And you need to make sure that's not going to be 0. So I'm going to set the denominator equal to 0. And I'm going to put someone on the spot here. I haven't had anyone from, let's see, I've had Matthew, I've had Nathan, I've had David, I've had Jalen. So it's going to have to be this table here. I've had Daniela. Did you volunteer? Yeah. So who over there is going to volunteer this when this is true? What? I'm saying we have to be worried about this happening, right? This could happen, be a problem. When does that happen? Solve that equation is what I'm getting at. What did you do? X to the fourth is negative 1? Fourth root. Anytime you do fourth root, you have to do plus or minus, don't you? Fourth root of negative 1. Liz? Fourth root of negative 1. What's the square root of a negative number? It's imaginary. Well, same with fourth root. Fourth root is also imaginary. And sixth root is also imaginary. It's impossible to raise something to the fourth power and get a negative number. So this is an imaginary number. That means that this will never be 0. It won't, unless we use imaginary numbers, which we're not going to. So that's never going to happen. We're never going to get division by 0, are we? So the answer's all real numbers. Here's another way to look at it. If I have this, is it ever possible for this to be 0? Well, I have 1, right? So I'm starting with 1. And I'm going to add to it something to the fourth power. Something to the fourth power has got to be positive, right? How can you ever add something that's positive to 1 and get something that's 0? You're not going to be able to, unless that's a negative number. But it can't be. So there's no solution here. The answer is the same as part B, all real numbers, negative infinity to infinity. All right, what about part, I think I'm going to let you do D and E. Let's say that D and E are to be turned in next class, which isn't till when? Next Wednesday. You get a holiday. So next Wednesday, turn in parts D and E. It'll count as a quiz grade. Just turn it in at the beginning of class. Find the domains for D and E. I don't mind if you get help. That's okay. I don't mind if you work together. If I tell you to do something at home, and unless I specifically say, work on this alone, then I don't mind you getting help. But that doesn't mean just go find someone to say, hey, my cousin's an engineer. Can you do that for me real quick? Figure out how to do it yourself. All right, F is the hardest one. F always causes problems. But it is critical that for you going on doing more math, that you understand how the complexity of this problem, or how complex this problem actually is. There's a lot of work that has to be done for this. All right, so you all ready? Paying attention? We got like 20 minutes left. I don't want to have to be like, remember I told you that problem to pay attention. This is, All right, so we see here what sort of issue? Square root problem, right? So we need to make sure that the radicand is greater than or equal to 0. So I need to make sure that this is greater than or equal to 0. We need this, right? We need that radicand to be greater than or equal to 0. Now, we did something like this a minute ago. And Matthew told us, Matthew or Matt? Well, Matthew, okay, yeah, that's what you have written down. So Matthew told us that it was an inequality, remember? And I said it was a linear inequality. And I said those are pretty easy, but you got to be careful because of if you multiply both sides by -1, it flips the sign over, right? That's the way linear inequalities work. This is not a linear inequality. This is called a quadratic inequality. And every student moving on needs to know how to solve a quadratic inequality because it is not as simple as students make it. And it can get you into a lot of trouble later. So here's how it's done. The first step into solving a quadratic inequality is to go ahead and make it an equality. Make it an equation first. Right? So that's where I'm going to start from. I'm going to just check. I know I want to know when it's bigger than or equal to 0. First, I'm just going to look at when is it equal to 0. And that's a quadratic equation. And that we know how to solve, right? We could either factor or use quadratic formula. In this case, I believe it does factor. I hope it factors. 2x, x, and then plus 1 plus 4. So we get our solutions, our factors. Now we set each of those factors to 0, right? So we get 2x plus 1 equals 0. That's one thing I'm solving. X plus 4 equals 0. That's another thing I'm solving. And I get two answers. What are those two answers? X is negative 1/2, and x is negative 4. Okay. We have not solved the quadratic inequality yet. All we have done is said where it's equal to 0, right? Step 2, after you find these solutions. Step 2. Can I erase this?
Yes.
Yes? All right. Step 2, plot solutions on a number line. We know that at these points, at negative 1/2 and at negative 4, we know that this inequality is true, isn't it? This is true at those 2 points? Because this thing is equal to 0 at those 2 points. Yes? So I'm going to put those 2 points here. I'm going to put them nice and solid. These are part of my answer. Those 2 points are part of my answer. But there's more than that. So what I want you to imagine is that those 2 points break up your number line into 3 sections. You have the section to the left of negative 4, the section between negative 4 and negative 1/2, and the section to the right of 1/2, or negative 1/2. And our question is, do you include everything over here? Does that section, does stuff to the left of negative 4 get included or not? Same with the stuff in here. Do we include that or not? Do we include this or not? Well, there's really only one way to do it, to actually check to see if that's true. And that's to actually test something and see if it works or not. So we're going to plot these solutions on a number line, and then we're going to test points. So let's see. Who wants to give me a point to the left of negative 4 to check that region? Anything you want. Negative 5. Okay, so I'm going to come over here. Somewhere on here, my number line is negative 5. And what I'm going to do with that test point is I'm going to plug the test point into the original inequality. So come back to the original inequality, and let's plug negative 5 in here and see if it works. So I do 2 times negative 5 squared plus 9 times negative 5 plus 4 greater than or equal to 0. And I'm actually asking myself whether or not that's true. Is it or not? What's negative 5 squared? 25 times 2? 50. So I have 50. 9 times negative 5 minus 45 plus 4 greater than or equal to 0. Is that true? Yes, it is. That is true. Which means that everything over here works. Everything that way works. So what I can do is imagine that everything over here will be part of my answer. Then I have to check another number in the second region, and then check another number in the third region. So let's check something in here. What's a number in there? Negative 3. And go through the same process. And this time, when I plug negative 3 in, I get 2 times negative 3 squared plus 9 times negative 3 plus 4 greater than or equal to 0. Yes or no? No. Because we get what? 9, 18, take away 27, add 4? 18, take away 27, add 4. That is not greater than or equal to 0. Which means that everything in here does not work. So this section fails. And then we would check another point. What would be the last point that we have to check? Anything we want over there? Yeah, anything here I could use. I think I heard -1. Remember, -1's over there. Be careful. So 0 is always an easy one to check, isn't it? 0 is pretty easy to check. Right here, you get 4 is greater than a 0, greater than or equal to 0, so that works. Which means that everything over here works. Forever that direction. Now with quadratic inequalities, it usually alternates, like yes, no, yes, or it would be no, yes, no. But we want to get into a habit of checking each region, because if it wasn't quadratic, if it was something like a cubic or 4th degree inequality, you would have to check all the regions. All right, well, how do I write that answer? Parenthesis on infinity, always. So, and then to -4, bracket that time, yep. Union, bracket, -1/2, and now forever. Infinity, parenthesis. That's your domain, written in interval notation. What's that? The union is just a way of saying, look, you've got a basket, right? This is a basket full of numbers, and you have another basket full of numbers, and the union just says those two baskets together is your answer. When we have sets like intervals are sets of numbers. When we put them together, we don't put a plus. The union is like the operation we use to tell you to put them together. Okay. Any questions on that? That one's more involved. Guaranteed you're going to have a problem like that on a test. Everyone here needs to be able to demonstrate they can solve a quadratic inequality.
Is this like a final?
Hmm?
Like, questions?
No? Yes?
When are we having this test?
We're having a test the Monday. We're coming back next Wednesday. We're having the test the following Monday. Is that correct? Or well, no, not. Yeah, the week after. The 21st. I need to double check on something on that, but I believe. Double check something on that. I scheduled that test because I have a commitment that I made like midway through the summer that lands on that Monday. I believe it's that Monday. It might be the Monday before. So we'll see. Let me double check everything, but it's supposed to be on the 21st, our first test. All right, we still have what, 10, 12 minutes, and I know you really are enjoying this stuff.
Good job explaining everything.
We still have a lot to do. I think that, let me talk about the difference quotient. This next thing about the arithmetic of functions is just about adding, subtracting, multiplying, and dividing functions. And then on this example, I give you some functions, ask you to add them, subtract, multiply, and divide. And I can do that probably next class. But I want to go and talk about this 3.1.11, a very important thing called the difference quotient. And so how many of you, again, have to do Cal 1? Cal 1? Okay. This is really kind of the heart of Cal 1 right here, this idea of a difference quotient. So here's where it all comes from, all right? If somebody gives you a function, I'm going to show you with pictures first. Remember first, before I begin this, the slope of a line is rise over run. Everyone remember that? Rise over run. Okay, so take a look at this picture I have here. I know this looks crazy, but just bear with me for a second. Right, so we have we have a function here. You see this function, this curve? Yes, okay, thank you. So you see this curve, right? And if I go and I take this point x, right, and I plug it into the function, then I create the y coordinate, don't I? And so I wrote it up there, and I'll write it up here also. X, f of x. This is an x coordinate, this is a y coordinate, right? X and y coordinate. And so if I move the x, if I were to change this x, the height would be different, right? Depending on where it is? Yes? But at some arbitrary value of x, the height of it is f of x. All right, no problems? I'm going to pick another point, a second point over here. And it's going to be whatever this x is plus something, like h. So imagine that this x were, let's just say that that x value right there was 2. Maybe this is 2 plus 2, which would be 4. Maybe it's 2 plus 1, which would be 3. It's just a little bit more than x. You still understand? If I take that value, x plus h, and I plug it into the function, it's going to be up here, this height, right? Which is the second point. There's my first point. The second point will be, what's the x coordinate? X plus h. What's the y coordinate? The function evaluated at x plus h. Y'all understand that? Yes? Those are those 2 points that I have up there. I didn't draw the curve. Now, we said that the rise over run, right? If you have 2 points, you can find the slope. Rise over run is going to be, this slope right here will be the rise this way over the run this way. Now, rise is the height of this point, the height of it, minus the height of this point. So won't that be f of x plus h minus f of x? So this triangle I just drew right here, this distance from right here is this y coordinate. That's how high this is. Take away this height. Maybe if I give you some points, it'll make more sense. 1, 3, I'm just making these up, 2, 5. How high is this side of the right triangle? 2. What are you doing? How are you getting that this is 2? y2 minus y1, right? 5 minus 3 is 2. So this would be 2, right? But if I didn't give you 5 and I didn't give you 3, then wouldn't it be f of x plus h minus f of x? And that's what that says up there. See it in purple? Okay, then how much is the run? Well, here it would be what? Take the 2 and subtract the 1, and then this side would have been 1, wouldn't it? But if we don't know what those values are, won't it be this x plus h minus the x? And what's x plus h minus x? Is just h, right? So that's why I'm saying here, x plus h minus x is h. All right, so with those 2 points, I create a line. The slope of that line is this expression right here. F of x plus h minus f of x, that's rise over the run we said was just h, didn't we? I could do that with any function. I draw a function, I pick a point x, I pick a point x plus h. I can always find the line through them, and it would always have that slope, right? Yeah? Theoretically? Now watch this. This is what we're going to do in calculus. What we'll do in calculus is we'll take that second point and we will start making it get closer and closer and closer and closer to the original point. Right? So notice that that line, that slope is behaving pretty erratically, right? It's like it's up here. First the slope is positive, then it's what? Negative. And then watch what happens. I get closer and closer. And everyone understand what I mean is I'm letting this second point get closer to the first point? As these get closer, do you agree that that line is starting to get really close to some weird line that just barely touches at one point? Right? What happens if I move that point right on top of the other one, though? What happens? Well, think about it. What's rise over run? If I take 2 points, right, If they're different points, then I can always get a rise over run. But what if it's the same point? So I just give you a point. I tell you the point's 1, 3. And I say, what's the rise over run? It's the same point. So the rise would be, how much do you go up by? Nothing. Divided by the run. What's the run? Nothing. What's 0 divided by 0? That's why you take calculus. You go figure this out. But do you understand that geometrically, that looks like that line is starting? I mean, there is some slope there, right? It's positive. Like, definitely, as I get closer, that slope is a positive slope. It's not a negative slope, and it looks like it's getting closer and closer to a certain value. So what is important for us in this class is not the calculus part of this. The important thing for us is to be able to algebraically figure out what this is. For any function that someone gives us, we need to be able to figure out that thing called the difference quotient. And so that's what we would do with these examples. Where are they? So I'm going to do the first one. I know y'all want to pack up, but I still have 3 minutes. So given a function f of x, the difference quotient is always f of x plus h minus f of x over h. And you should have that probably put into the memory. All right, it's that important that you should memorize that formula. So it does not matter what function someone gives you. As soon as someone gives you a function, you can always compute the difference quotient by figuring out what this is. So I want you to just look at some things here. Didn't we look at this already? Wasn't that part f of a problem we did earlier? What's the argument of that function? X plus h. So this first part of the difference quotient is just plugging x plus h into the function you're given. Once you figure out what that is, then you come in here and you subtract what? The original function, which someone is going to have to give you. So there's really no work that you have to do this part. You have to do a little work to do this. And then divide by h, and h is just h. So let me now show you a specific example of part A. I'm going to give you the function now, okay? Here's the function I want us to find the difference quotient of. And this one should look familiar, right? Or did we do this one earlier? No, this was a different one, sorry. There's a function. There it is. I would like for us to find the difference quotient. Can I call it dq? That's what you like about Texas, right? dq. Finding the difference quotient. So I'm going to set up this ratio. You ready for me to do it? All right. Would you agree that you could look at the difference quotient as being two pieces, top left and top right, all over h? So you have like the top left minus the top right over h. You see that? Okay, let's fill in the pieces we know for sure. F of x. That's given to us in the problem. So why don't we fill in this top right one with f of x? And very important that I use those brackets, because that negative sign is going to have to do what? Distribute through. The real tricky part of this is figuring out what this piece is, which is f of x plus h. So maybe what I should do is do it over here, get the answer, and then plug it in. So like a little bit of scratch work on the side. What is f of x plus h for me? So I take this, I plug in x plus h. Negative 2 x plus h squared minus x plus h plus 3. Replace that with x plus h. Replace that with x plus h. Make sure, because there's a minus, that you put it in parentheses right there. And then plus 3. And we clean that up, don't we? We square the x plus h. We distribute the negative sign through. I'll put it up here. So this would be negative 2 x squared minus 4xh minus 2h squared minus x minus h plus 3. So I've done all the work here. I've expanded this out. I've pulled the negative 2 through. I multiplied the negative 1 through, and I get that. Do you all understand where that came from? That's the top left of the difference quotient. So negative 2x squared minus 4xh minus 2h squared, minus x minus h plus 3. I'm going to move my bracket. I didn't quite give myself enough room here. Minus x plus 3. I'm out of time, but let's see what would happen. You distribute the negative through here, right? This would become what? A positive 2x squared? Yes? Yeah, this negative becomes plus 2x squared. That would cancel with this negative 2x squared. So this one and this one are going to go away after I distribute through. What about the x? It's going to be positive x, and don't I have a negative x here? Those cancel. What about the 3? It becomes a negative 3, and there was a positive 3. That cancels. Everything there cancels. The only thing left is negative 4xh plus 2h squared minus h. Oh, I said plus. And then all over. Okay, what do all of those have in common? An h. So can't you factor an h out and cancel it? So in the next line you'll have negative 4x, 2h minus 1, because that h cancels and you get a 1. This is the difference quotient. You notice that last step where we cancel the h? You should always get that h to cancel. If that h doesn't cancel, you mess something up. All right, I'm out of time. Let me just tell you on your homework. You can come up here and grab it. I'll put the quizzes on this table. I'm going to let you go. I'll send out an email about the homework if there's anything special, like about skipping certain problems. So pick up your quiz if you want it. Anybody need a copy of the calendar? The new, fresh copy? Y'all have a good extended weekend. See you on Wednesday. Don't come all wiped out. Try not to be all... Try and remember some of this by the time we get back.